In this video, I want to go over how we get values into our digital systems from the analog world. So to start that, let's talk a bit about how the data is stored on computers. So data is stored in computers as bits, collections of individual bits at the digital logic layer of our machine. Each bit has a single value, either a 0 at any given moment or a 1 at any given moment, represented by some low or high voltage internally. But what matters to us in computer science is that this value is one of two different unique values. So we have a 0 or we have a 1. And that could mean things like false and true. It could mean things like red versus blue, if the only things we needed to record were red and blue. Now, if we have multiple bits stuck together, so given n bits, however many bits that is, with that many bits we can store 2 to the n different values, whereas the entire bit pattern of n bits, there are 2 to the n different unique bit patterns where each of the bits has a 0 or a 1 in it. So with 8-bit numbers, we can hold 2 to the 8th, which is 256 different values. And with a 10-bit number, just as another example, we can hold 1,024 different values. Right? And those would be represented by the bit patterns starting with all zeros, going up to all ones, and everything in between. Now this is excellent if we want to track discrete values. So as an example here, I say how many apples are on the table. And over here I've got a picture of 4 apples. And we would definitely say that this is 4 apples. But I want you to understand that this aspect of our lives is definitely discrete. So when I say how many apples are there are clearly 4 apples. But if we take notice, this apple here is larger than any of the rest. And this apple here is smaller than any of the rest. But we don't say that there are, 2.89 apples or 3.47 apples or something like that. When we ask a simple question like this, the value we're looking for is 4. Now that's great, but if we wanted to measure something more specific about the total amount of apple we have, we might ask a question like, how much is the total weight of the apples on the table? And at this point, we get into a different realm. We're no longer in the discrete realm. We are in the analog realm. And the world is mostly analog. Obviously, since we just had a discrete example, it is not totally analog, but it is mostly analog. And this effectively just means that things exist over some continuous range. So the height of a person is always a specific height at any given moment, but as they are a growing child, that height changes instantaneously by a very, very tiny amount. But it is a discrete, it is a unique new height, right, from moment to moment. And when we deal with data that is continuous, that is analog, there is no finite set of discrete values, whether we have 8 bits or 10 bits or 1,024 bits. No set of discrete values that's finite is going to be able to represent each of the possible analog values we might experience, because they are infinite and our set by default is finite. So to deal with this, we have to do something called analog to digital conversion. This is where we introduce specialized equipment of some sort that is able to experience the analog world through some stimulus and then produce as output a discrete value that fits into a finite set of discrete values. So we might have a really inexpensive microphone, for example, that's really just recording volume levels of some kind and within a very restricted range. And so it might produce a 16-bit value, which would give us some level of volume between 0 and approximately 64K. All right, so as a part of the analog to digital conversion process, there are a couple key words we need to know about. One is sample. We sample analog values, which means we capture a digital version of it at a particular point in time. Now, how often we do that, or how regularly we do that, is known as the sample rate or frequency. And that has a dramatic effect on how accurate our measurements are, particularly if our goal is to look at the change in some value over time. Now, we also have some resolution to the sampling that we do. So we have a sample resolution. Because what the analog to digital converter is actually doing is it's taking the infinite world of values and squashing it down to some finite range that's represented on one end, say, by all zeros, and possibly on the other end by all ones. But there's a discrete number of, or a finite number of discrete steps in between each of those. I'm going to do a bunch of examples here on paper to make all of this clear, as well as talk about some of the big issues related to analog to digital conversion. And we're going to go off of a real basic example here. This nice quote at the bottom, which is not really a quote unless you attribute it to me, and that's that I like to grow peas. If you remember from your grade school days, you learned about the Punnett square and Gregor Mendel and his pea plants and how he was studying genetics. Now, genetics is out of the scope of this particular conversation, but I happen to have a garden that I love tending to, and I particularly do love to grow peas. So in my garden, I have a raised bed of dirt within which I plant seeds at a fairly consistent depth at regular intervals. And over time, with sun and water and care, the pea plants grow up these strings that I've set out for them to grow. Now, since I grow these plants from year to year, I want to have the best plants that I can each year, and so I keep the seeds from the plants that I grow. But I actually do take measurement of how tall each of my individual plants is over time, because I want to know which plants grow the fastest, because a tall pea plant is going to tend to have more leaves, so it's going to get more light energy and produce more pea pods potentially earlier and potentially with greater nutritive value. Now, I'm no botanist, so I'm just making some assumptions based on what I learned in grade school, and I sure have a good time doing it. But these plants don't grow that fast. If you were to stand in the yard and watch them, you wouldn't be able to perceive any particular difference in their height from moment to moment. So whenever we do this kind of thing, whenever we're trying to take measurements from the analog world and bring them into the data world, we have to deal with this concept of rate. So we have to concern ourselves with that sample rate, right? How often should we bother to measure these pea plants? Now, once the pea plants poke out of the ground, they actually start growing relatively quickly. And so I do this about every 4 days. That's my sample rate. We also have to concern ourselves with the sample resolution. The sample resolution is how far apart are the individual measurements that we'll take. So I might go out there with a yardstick or some other tool like that, and that means I can only take measurements as accurately as my yardstick or my ruler actually shows variation. Right? So we have to pick something like this, and I'm fairly lazy and use an imperial ruler for this, and so I do things on the order of about 1/4 inch. So my sample resolution is about 1/4 inch. But these are important decisions, because I have to log this information somewhere. And if my sample resolution is only 1¼ inch, I only have to write down numbers like so many inches, decimal point 0, or decimal point 25, or decimal point 5, or decimal point 75, right? Of course, I could do that as fractions as well, but if I were storing the numbers like this, even just on paper, if I wanted to go to 1/8 of an inch, I would need to increase the amount of physical space that I consume for each number that I record, because my resolution is finer grain. Now, if I were to mess around with sample rate, say try to offset my higher resolution by taking fewer samples, taking them less often, I'm going to miss an awful lot of data. And if I want that data, and maybe I want lots of it, I can increase the sample rate so that, or decrease the delay between the time I take samples. And maybe I do this every 2 days. But if I go from 4 days to 2 days, I've effectively doubled the total amount of storage. So my storage requirements suddenly increase. And while that may be good for the science that I might be doing related to this data, it's not necessarily great for the cost of whatever is required to maintain this information. So this is the basics of the types of things we would be doing in the real world. Now, what I want to do is look at some other basic kinds of signals that we'll encounter. So we're not always just measuring pea plants. If nothing else, pea plants, their height tends to go up monotonically, meaning they continue to go up and never suddenly get shorter, at least not by growing anyway. But there's an awful lot of other kinds of continuous signals that we might want to look at in the real world. As an example, we might have a signal that looks something like this, a wave that goes up and down in some fashion. Not in any way predictable, but a nice, smooth, continuous wave. Now, that particular waveform, if we're going to sample it, we have to have a sample rate. So I'm going to represent that sample rate with some thin vertical lines. And I'm just going to draw them somewhat arbitrarily. It doesn't have to be perfect here to get the idea across. And so as time moves forward this way, we're going to take a sample at this moment, this moment, this moment, this moment, and so on. And when we do, we're going to have to record the value within the constraints of our resolution. So we have, first of all, a finite number of discrete values that we can hold, and then our resolution determines the distance between these discrete values. So I'll just add some lines to go across like this. And so our resolution is here. So these are the values that we can represent. Okay. Now, as we take samples at each of these given moments, we'll notice right away here in this, possibly easier to see on this one, where our actual waveform crosses the moment in time that we want to take a sample. We're not on one of our actual discrete values, neither of the two closest. So we have to pick one of those. And there's really two ways to do that. The first way, which is by far the most common, is truncation, which I'll demonstrate in blue. So we'll use truncation. In truncation, we basically clip off all the low-end bits, and it's kind of like when you do division in a calculator when you were younger, integer division, and you lose the decimal portion of your values. So we're effectively going to take the point at which our wave crosses the line and then go down. So this one crosses here, this one crosses here. At this point in time, we'll cross right here. This one, while it's very close to here, we'll actually represent it as this value. This one will be this value. This one's really close, but it looks below it to me, so I'm going to pick here. And this one is, let me represent represented here, and this one here. So those would be the unique values that we would actually record if we were, excuse me, if we were using truncation as our mechanism behind the analog to digital conversion. Another that we can do is rounding, and it's fairly obvious, right? That's another thing that would allow us to get values that are at least, hopefully, closer to the real values. So I'll draw those in red. I'll put it kind of right next to it. So here's a red value for this one. It's definitely closer to this one. I'll say this is closer to here. This one, closer to here. This one's definitely closer to here. This one is right about there. This one's definitely closer to the one above. And this one to the one below. And this one to the one above. Now, right now we just have a bunch of colored dots, and it's not so easy to see the waveforms that these represent. And so I'm going to show those in two different ways as well. And I'm going to use the same two colors just because I only have so many colors handy. But one of these is going to be a discrete representation, which I'll do in blue. And in the discrete representation, we're effectively interpolating the values between each of our readings linearly. So, or along the same path. So we go from here to here in time, thinking that every value between here must have been the same. Same here. Same here. And this one continues forward. This guy goes to here. This guy goes forward. And this guy goes forward. So they just stay at whatever value they were until we get a new sample. So we have this kind of spontaneous, choppy version of a waveform. Right? That's the discrete method. The other method that we'll use to interpolate the data between there is just a linear representation, and that'll be the next simplest. And I'll do this in red. And just to be clear, when I did the discrete ones, since I was using the blue marker for that, I only did the discrete interpretation or interpolation on the original truncated values, which were also in blue. Now I'm going to do a linear interpolation on the rounded values, just because they're the same color. But we could have truncated sampling with linear interpolation if we liked, and you'll perform something like this on your homework. So now between this red and this red, everything stays the same. But then between here and here, we're just going to interpret this waveform linearly. Same here, but they're the same value, so it's a straight line. Then we get a curve that goes up like this, and then one that goes here, and then a nice sharp one down to here, and a slightly less steep one up to there, going wherever it might be after this. So there are a few problems that we'll conclude with related to doing this kind of sampling. The first is the finite resolution. Right, so this is a big deal, the finite resolution. We have, over time, when we take our samples, a high value and a low value here in this simple drawing, and then we get some kind of a line like this. That's the actual waveform, but really we're picking between these different values, and even if I'm using rounding, I'm still not really accurately representing the original values. So we just have inaccurate values. And that's just fundamentally what we're going to get. The second real problem is aliasing. Right. Now in aliasing, we can get lengthy misrepresentations of data. So we might have a wave that looks like this. Real nice and smooth and regular. And then we come in with the points in time that we want to read this wave. Like so. These are the moments we'll do it. And we're going to pretend we have infinite resolution here. And we'll just mark off where these things cross, like so. And now I have an approximation of the wave I experienced. You see, and it goes up and down at a much slower rate than the original one. So the aliasing causes lengthy misrepresentation of the data. The third one that we're going to have is that we're going to miss anomalies. And I'll give you an example of this. We could have two moments in time, a nice smooth curve, and then some kind of sharp change in value, and things like this. But we're going to find these two values, and we will have entirely lost that one. So we will miss anomalies. And the fourth and last most important problem here is that we might overemphasize the anomalies. And so we'll just say overweight the anomaly, or overemphasize. Now this happens whenever we actually have anomalies at the moment of sample. So we might have a nice curve that's going down like this, and then some crazy anomaly here, another weird anomaly here that we're recovering from as we go up. And as a side effect, we read a waveform that looks like this, which is very different from the actual waveform. So those are our four biggest problems with analog to digital conversion.